Maya Lochi here, and in this video I will teach you everything you have to know about SN1 and SN2 reactions. These reactions are nucleophilic substitution reactions, which means that our starting material will have a leaving group, and I will show you leaving groups later, but usually a good leaving group is a halogen such as chlorine, bromine, or iodine. And we will have a nucleophile which will replace leaving group. So the product of SN1 and SN2 reaction will be nucleophile that replace the leaving group. Let's look at each reaction separately and see the mechanism, stereochemistry, and how to choose each one. Starting with SN2, this is a one-step reaction, so everything happens at the same time. For SN2, we draw two arrows. So let's say that this is my starting material and it has a leaving group on a dash, and I have a nucleophile here. In the first arrow that you will show will be from the bond to the leaving group. This arrow shows that the leaving group is leaving. So first, an arrow from the bond to the leaving group showing it leaving. At the same time, nucleophile will attack the carbon that had the leaving group from the back. So you will show an arrow from the electrons on the nucleophile to the carbon that had the leaving group from the back. And as you can see, we will replace leaving group with the nucleophile in this reaction. In terms of stereochemistry, because nucleophile attacks from the back, stereochemistry changes. It is an inversion of stereochemistry. So what you need to know is that if your leaving group was on a dash, you will show your nucleophile on a wedge. If your leaving group was on a wedge, you will show your nucleophile on a dash. If your leaving group was up, for example, then when you will show your nucleophile, it will go down. Nucleophile will be in the opposite direction. It will attach in the opposite direction of your leaving group. We have inversion of stereochemistry for SN2. This is very, very important to remember. Next, we're going to look at substrate preference. Substrate is the molecule that you're starting with. For substrate preference, SN2 prefers primary, okay with secondary, and never tertiary. What does primary mean? So for example, let's say we have a molecule and my leaving group, whatever that is, and a leaving group, let's show this leaving group, let's say chlorine. So chlorine is my leaving group. Let's see what carbon it is attached to. So this is the carbon that chlorine is attached to. How many carbons is this carbon attached to? It's attached to one more carbon. This is called primary. If, for example, my chlorine was here, how many carbons is this carbon attached to? It's attached to 2. So this would have been secondary. And finally, if my chlorine was here, this carbon that has chlorine on it is attached to 3 carbons. This is tertiary. So with that in mind, let's read the substrate preference. SN2 prefers primary, so it would prefer something like this. It's okay with secondary and never tertiary. Why is that? Well, nucleophile attacks from the back. So if there are a lot of groups in the back, it will simply not be able to reach the carbon that it's trying to get to. So if we have a tertiary substrate, if our leaving group is attached to a carbon that's attached to 3 other carbons, nucleophile will not be able to get to that carbon. So that reaction will not be able to happen. So primary substrate is preferred. Next, for nucleophile, we want strong nucleophile, and that means it is usually negatively charged. Cn minus, OH minus, RO minus. R is just an alkyl group like CH3O minus, CH3, CH2O minus. So R represents carbons and hydrogens here. I minus, RS minus are all strong nucleophiles. Sometimes they hide the nucleophiles by putting them together with a metal cation. For example, if you see NaOH, Na is a metal. This has a plus, this has a minus, but they will show it to you as neutral. You have to recognize that there is a plus here and a minus here. NaOH, strong nucleophile. If they give you any of the metal cations, Na, K, Li, these are all metal cations, and the second part will have a negative charge. KCN means K plus, Cn minus. LiOCH3 means Li plus, OCH3 minus. So if you see Na, K, or Li, give it a positive charge and the second part of the molecule will be negative. Moving on to solvent. Solvent is what nucleophile is dissolved in. For SN2, we want polar aprotic solvent. Aprotic means it doesn't have any hydrogens to give, and polar means the charge is distributed asymmetrically throughout it. But honestly, you can just remember some of these solvents. DMSO, acetone, DMF, CHF are all polar aprotic solvents. So if we see them, we will think, okay, this might be SN2 reaction. We have to think about it all together. Do I have a primary or secondary substrate? Do I have a strong nucleophile? And what kind of solvent do I have? So, for example, if I have a primary substrate, a strong nucleophile, a polar aprotic solvent, then this is going to be an SN2 reaction. For leaving groups, we want the best leaving group possible for all of the reactions for SN1, SN2, E1, and E2, which I will teach later. We want the best leaving group possible. So these are some examples of good leaving groups. I, Br, Cl, OTS, and OH2 are all good leaving groups. If you see them on the starting material, then you will know maybe I'm doing SN1, SN2, E1, E2 reaction because I'm starting with a good leaving group. In terms of kinetics, this reaction is bimolecular, which means the rate of the reaction depends on both substrate and nucleophile, so both are important for the rate of reaction. Rearrangements are not possible in SN2 because it is a one-step concerted mechanism. And this is an example. So for example, I'm looking at the starting material. I notice Br. Br is a good leaving group right here. Is it primary, secondary, tertiary? This carbon is attached to one more carbon, so that means I have a primary substrate. Next, I look on what's on my arrow. This is a strong nucleophile. OH minus is a strong nucleophile. So this must be SN2 reaction. What I do next is my electrons from OH minus attack this carbon, bromine leaves. It's all in the same step. Attack the carbon that has the leaving group from the back. Draw an arrow from the bond to the leaving group to show that it's leaving. And OH replaces Br. In this case, I do not have no wedges or dashes were shown in the original starting material, and this is not a chiral molecule, this is not a chiral center, so I do not need to worry about stereochemistry here. I can just replace my Br with OH and I am done. Let's go ahead and look at SN1 reaction now. SN1 reaction is a two-step reaction. Sometimes it's 3 steps. Actually, most often it's 3 steps. In the first step, leaving group leaves, creating a carbocation. This first step is the rate limiting step. So here I have my starting material. Lg stands for leaving group, and I will draw an arrow from the bond to the leaving group, and that means that bond is breaking, and this carbon is now missing a bond. It will have a positive charge. That's the first step. In the second step, nucleophile attaches to the carbocation. So nucleophile is going to attach, and these are the products. There is usually a third step, which I will show you once we do a real problem, where solvent takes off the hydrogen from the nucleophile in a step called deprotonation, and I'm going to show that to you very soon. For stereochemistry, we make 2 products. because when we go through carbocation, nucleophile could attack from top or from the bottom. You can either put nucleophile on a wedge or on a dash, which is called racemic mixture. So in SN1, racemization happens. We make two products. In SN2, we made one product. We had inversion of stereochemistry. If this was dash, this became wedge. In SN1, we make two products. One, our nucleophile can either attach on a wedge or on a dash. Next, in terms of the substrate, it has the opposite preference. SN1 has the opposite preference of SN2. SN1 prefers tertiary, so it wants the leaving group to be attached to a carbon that's attached to 3 other carbons. It's okay with secondary and never primary unless resonance stabilized. So why is that so? Because we want to make the most stable carbocation possible, and the more substituted our carbocation is, the more stable it is. So tertiary carbocation is better than secondary, which is better than primary. So SN1 prefers tertiary substrate to make a tertiary carbocation. Another thing that can stabilize a carbocation is if it's resonance stabilized, which means that it's usually, if it's next to a double bond, that will make this carbocation also happy because there is a resonance from the double bond next to it. And so if we can create a carbocation in what we call allylic position. Allylic position is a carbon next to the double bond. This position is called allylic. Then it will be very happy because it will be resonance stabilized. So here you see my little chart of increasing stability of carbocations, and the better the carbocation is, the more likely SN1 reaction is to occur. Because remember, the rate determining step is making that carbocation. So tertiary allylic means that I have a double bond and then the carbon next to double bond is attached to 3 other carbons like this, and it has a positive charge. So 1, 2, 3, and allylic means I can do resonance to it. Tertiary allylic is the best, followed by secondary allylic, tertiary alkyl. That means you're not resonance stabilized, you're just regular tertiary carbocation, and so on and so forth. So we want the best possible carbocation for SN1. Another thing that we need to look out for SN1 is the nucleophile. What kind of nucleophile do you want? Remember, for SN2 we wanted strong nucleophile, which usually had a negative charge. SN1 is the opposite. SN1 wants weak, usually neutral nucleophile. So honestly, most often nucleophile for SN1 will be either water, alcohol, or acid. ROH, again, R stands for alkyl group, which consists of any hydrogens and carbons. So it could be CH3OH, CH3CH2OH, cyclopentane with OH on it. Any sort of carbon chain or ring with OH will do as our nucleophile, or we could have an acid as well. For solvent, remember SN2 wanted polar aprotic solvent. SN1 wants the opposite. It wants polar protic solvent, something that can give a hydrogen, because that will stabilize the carbocation. Anything that will make the carbocation happy will help SN1 reaction. So for example, we have here H2O, CH3OH, CH3COOH. These are all examples of polar protic solvents, usually water, alcohol, or acid. Just like SN2, SN1 wants a good leaving group. All of them want a good leaving group. For kinetics, only the first step in SN1 reaction is the rate determining step. So it depends on the substrate only. So rate will depend only on the substrate. Rearrangements are possible, and we will have to talk about them in another lecture. And then finally, this is an example of SN1 reaction. And in this reaction, you can see the leaving group leaves, creating carbocation. Now our nucleophile attaches. And by the way, how did we know this was SN1? This was a secondary secondary substrate, and we have a weak neutral nucleophile, water. So if I see secondary weak nucleophile, I know I'm doing SN1. So again, first step, leaving group leaves. We show an arrow from the bond to the leaving group. Carbocation is created. Then our nucleophile attaches to the carbocation. When our nucleophile attaches, notice in this case, water attached, it has too many hydrogens. It has a positive charge. So there will be a third step to deprotonate, to take off one of the hydrogens. Whenever alcohol or water will attach, we will have a third step to take off the hydrogen. So here another water comes in, takes off the hydrogen. The bond between hydrogen and oxygen breaks, giving electrons here. And we have our product, which is replacing Cl with OH. And by the way, in terms of stereochemistry, we can have this either on a wedge or on a dash, because remember, we create a racemic mixture. Now let's go ahead and we're going to do two reactions. We're going to identify them as either SN1 or SN2. We will do the mechanism and we will predict the products. So let's get started. Let's say that I have this molecule. Let's say that I have this molecule first. And let's say that I use CH3OH. So what we're going to look at first is we're going to look at our leaving group. Identify, okay, Br is my leaving group. And what kind of substrate do I have? What kind of carbon is Br attached to? In this case, Br is attached to 1, 2, 3 carbons. This is tertiary. Next, I'm going to ask, what kind of nucleophile do I have? Is this a strong or weak nucleophile? This is alcohol, CH3OH, the same thing as I wrote before ROH. It's the same as ROH. CH3 is just an alkyl group. So is this strong or weak? This is a weak nucleophile. So together I realized, okay, I have a tertiary starting material, a weak nucleophile. This must be what? SN1. Now I can do my mechanism. SN1 is in 2 or 3 steps. Step number 1, leaving group leaves, creating a carbocation. Let's show leaving group leaving. Give this to the leaving group. Once the leaving group left, I will have a carbocation. Carbocation will be on this carbon. Let's not forget the methyl group, but now I cannot show it on a wedge or a dash because now I have a planar carbon. Once you have carbocation, don't show any wedges, dashes. Next, second step, my nucleophile attaches. I need to find an atom inside my nucleophile that has electrons that it can use to attach to the carbocation. In this case, oxygen. Oxygen can come in here. Let's go ahead and show that. But now my oxygen has too many bonds. It has 3 bonds. So, and it has a positive charge. So I need to have last step. And the last step, and by the way, all of these have to be equilibrium errors. And in the last step, I will deprotonate my hydrogen. So I'm going to use another one of my CH3OH. You can assume you have a lot of these molecules, and I'm going to take off the hydrogen. So from the oxygen to the hydrogen, give electrons to this oxygen. By the way, this had 2 electrons here. And let's go ahead and show our product. Our product will look like this, OCH3 or OMe. Now, if I wanted to show stereochemistry for this product, I started with my bromine being on a dash. Remember, in SN1, I make a racemic mixture. So I'm going to show my OCH3 being either on a dash or on a wedge. You make both products. So let's show both products. Oops. Let's show both products. Methyl group. And if OCH3 is on a dash, that means methyl is on a wedge. If OCH3 is on a wedge, that means methyl is on a dash. So that's my first reaction. Now let's look at another reaction. Let's say that I have this reaction, this reactant, and let's say that it says NaCN. Let's identify what kind of reaction it has. Let's say NaCN with DMF, for example. So first I say, what kind of substrate do I have? Is this primary, secondary, or tertiary? This carbon is attached to two other carbons, so this is secondary. Then for this is Na plus, CN minus. Remember, whenever I see a Na, K, or a Li, I'm going to give it a plus. The second one is a minus. This is a strong nucleophile. CN minus is a good nucleophile. It has a negative charge. Usually when we have a negative charge, it's a good nucleophile. Finally, I see DMF, and I know DMF is polar aprotic solvent. So all of this leads me to determine that this is SN2 reaction. Remember, SN2 reaction happens in one step. It's concerted. The leaving group leaves, so I draw an arrow from the bond to the leaving group. So these electrons are going to the iodine, and then the nucleophile attacks from the back. So I'm going to draw an arrow from the back like that. And to predict the product, I simply replace my leaving group with my nucleophile. And remember, we have inversion of stereochemistry. Stereochemistry changes. So I'm going to give it a dash. Oops, this is not O. This is a CN. And this is the product of my SN2 reaction.